Alright, this is a review problem for a Butterworth low-pass filter IIR design. Okay, in this problem you're supposed to use the bilinear transformation, but really we've developed all the theory for that, so you don't really need to know anything about the bilinear to actually do this problem. But, I do want you to know where it comes from. So, it's the bilinear transformation and a low-pass analog Butterworth prototype to design a low-pass filter that operates with a sampling rate of 40 kilosamples per second, has a pass band specification of 10 kilohertz. I'm sorry, that's the edge of the pass band in frequency, 10 kilohertz. Then the attenuation has a maximum of 1.5 dB at the edge of the pass band. And then the stop band begins at 15 kilohertz and is at least 35 dB. Okay, so what we're going to work on is, first of all, let's find the order of the filter and the 3 dB cutoff frequency, omega naught. Okay, so we go through here, and really it's just an application of these formulas. It's pretty straightforward. You calculate these numbers and you get there. All right, so let's get started. Okay, I'll move this formula down a little bit. All right, so what we need to do first is convert the analog specifications to the digital domain. Okay, so that means we find omega pass. That would be 2 pi f pass divided by f stop. I'm sorry, fs. Not f-stop. Okay, so you calculate that number. Okay, and I did that in MATLAB and get 1.5708. All right, then we do the same thing with omega stop, normalized frequency, 2 pi f-stop divided by fs. F-stop is 15 kilohertz, fs is 40 kilohertz. Plug the numbers in, you get 2.3562. You can check that. All right, from there, you need to calculate omega in the analog template domain. So omega pass. All right, and that, according to the formula, we pre-warp, right? You pre-warp because you're going to use the bilinear transformation, and that would be taking the tangent of omega pass that we calculated and divide by 2. All right, so we get omega pass that way, and I get that number to be 1. Okay, and then omega stop is calculated in a similar way. Okay, and so I get capital omega stop to be 2.4142. All right, so we have these parameters, and then to calculate the order of the filter, we're going to need to also calculate, if you look at the formula, epsilon stop and epsilon pass. All right, so those are given by this box up here. All right, so epsilon pass, epsilon stop. Those are given from the stop band specification and the pass band specification. Okay, so writing that down, we know that epsilon pass is the root of 10 to the a pass over 10 minus 1. And when I calculate epsilon pass, I get 0.6423. All right. Then when I calculate epsilon stop, right, so for epsilon stop, I get square root of 10 to the a stop over 10. A stop is 35, minus 1, and take that square root, and what I get for that number is 31.6070. Okay. All right, so from there you just plug epsilon pass, epsilon stop, and omega pass into this formula. and you get a value for inexact of 4.42, and we know that this is really required to be an integer, so we round up so that we meet our specifications. We round up to the nearest integer that's, use the CEL function, the nearest integer that's bigger than 4.42. Okay, so that gives us the order, all right, and from there we can calculate the cutoff frequency, all right. So the cutoff frequency of the filter, you can use either the formula for the pass band or the stop band, depending on your preference, or you could use somewhere in between. Okay, but that formula, let me look that up. This formula was derived by just simply plugging in to the constraints on the Butterworth filter, and we get that omega naught, okay, the 3 dB frequency of the Butterworth filter is omega pass divided by epsilon pass to the 1 over n, where n is 5 in this case. Okay, so we can calculate that. I didn't do that yet in MATLAB, so hang on. Omega naught and the number I get when I plug that in is normalized frequency of 1.0926. Okay. All right, so I'll need that in the next stages where I have the formula for the coefficients. What I'll need is omega naught and also the thetas. The thetas are a function of the order of the filter. Okay, now that we know n and we also know omega naught, it's possible to compute all the Butterworth coefficients for each of the stages. Okay, but to make this work out easiest, what I do is I visualize how many thetas I'm going to have. I think that's easier than applying the formula in the book where you have to figure out the value of I and all that kind of stuff. I think it's easier just to think about it first. How many thetas do you need? Okay, so if I'm going to have a 5th order Butterworth, okay, that means I'm going to have 10 poles around this circle of omega naught. And remember, we only take the left half plane poles. Okay, so if I was going to divide this by an odd number, I know I have a pole here, and so then I would have a couple of pairs here and here, and here and here. And then I'd just repeat that on the other side. So what that tells me is that I have 2 pairs of complex conjugate poles and 1 real pole. All right? So the real pole is clearly at the angle pi, so theta is equal to pi. But if it's equal to pi, you're just going to have a first order section. So anytime there's an odd number of poles, the Butterworth filter technique ends up with one of the sections being first order. And if it's first order, this is the form of the transfer function. All I need then is the g's and the single A01. All right, so at that point, you just plug into the formula for that, okay? So the formula for that is right here for G0 and for A01, okay? I do that here in a second in MATLAB rather than just write the numbers down. I'll show you what that is. Okay? Well, once you know that, the formula for the thetas is theta is equal to pi over 2n, n minus 1 plus 2i. And what I know then is that I goes from 1 to 2 from this picture. That's the reason I draw the picture, is to find out how many i's I have, how many thetas. Okay, so I know I'm going to get 2 thetas coming out of this. Okay, so I plug in, n is equal to 5, so this would be pi over 10. All right, n minus 1, 5 minus 1 is 4, plus 2 times 1. Okay, so one of the angles is 6 pi over 10. All right, now that'd be theta 1. Theta 2, the second pair of complex conjugate poles, would be pi over 10. Okay, n minus 1 is 4, plus 2 times I, 2 times 2 is 4, so I'd get 8 pi over 10. So at this point I have the theta, and I also have omega naught, which is all I need to calculate each of the coefficients for second order sections. All right, I've got 2 second order sections, 1 first order section. It's just a matter at this point of plugging in the numbers and getting these coefficients, okay? Now clearly on an exam, it would take way too long to get all those, but I do think it's important that you know where this come from. So let's look at what happens if you plugged it into a calculator or plugged it into MATLAB. It's just implementing these formulas, okay? So there's the formulas. I get the first order section coefficients here, okay? And then here's a theta value. All right, so theta is 6 pi over 10. Here's the formula for the coefficients. I plug those in. I get A values back out. And here's the second of the second order sections with theta equal 8 pi over 10. And you get the third set of coefficients. Okay, that's tedious to do. You know, I plug the numbers into MATLAB. You can plug those into your calculator, make sure you know how to do it. On an exam, I wouldn't ask for all these numbers, but maybe I would say, okay, if theta is equal to 6 pi over 10, what is G1, and what is A11, and what is A12? That would be a reasonable thing to ask on an exam. You'd have time to do that. So make sure you know how to do those calculations. All right, so the last part of the problem was to write a cascade realization of these second order sections. We did enough of that on exam 2, so let's just scratch that problem from this review. All right, so hopefully you find that helpful for Butterworth filters.